So processes are like is a concept in combinatorics. If you're It's used in combinatorics games mostly. So like if you have a given state and you want to reach some required state, you need to do some steps to do that. So the bunch of steps that you perform are is basically called a process. So we'll start with an introductory problem. I'll give you a few minutes to try this. If you get any ideas, you can DM me.
So how many columns do we have in this configuration?
You have as many columns as you know.
So only like any pebbles, like they can be like arranged in any possible um, number of columns.
Like for example, if you look at say n equals 3, then in the initial state you have 3 and then nothing beyond it. Then in the next move you can do 2 and 1. And now since there is no pebble can be moved, this is the final configuration. So like if you had, let's say, I don't know, 20, so you could move them for as many columns as
Okay. So they like start with n pebbles in one column, right?
you. Yeah.
Okay. Cool.
Okay, so any ideas? Invariance. Okay, interesting. What kind of invariance are you thinking of?
Like the number of pebbles is constant, but
Yeah,
like that's not of that much application.
true. I don't think that would lead to much. So first, let's try with a few small cases. For n equals 1, we have 1, which is just the final configuration. Left to right number of pebbles are decreasing. Yes, that is true.
What if we look at the differences between the number of pebbles and the piles?
Yes, that's a good idea. So like if the difference is greater than 2, then you have that the difference reduces by 2, right? Like for example, you have 2 and 0, let's say. So this will become 1 comma 1. So the difference between two piles after remove will always reduce by 2. So let's look at some uh, small values of n. So for 1, this is the final configuration. Then for 2, it will be this. For 3, it will be 2, 1, as I showed you. Sorry, for 2, it will be 1 comma 1. Then for 4, this will go to 3 and 1, which will then go to uh, 2, 2, which then goes to 2, 1, 1. Monovariance on the consecutive difference between piles. Yeah, that is the general idea. So, but could you like be a bit more specific? Like, what exactly are you considering?
I joined a bit late. What is the problem?
This is the problem. If you want the source, it's 2001 C7.
Okay.
So for 5, it goes to, you can go to 4, 1, then 3, 2, then 3, 1, 1, and then 2, 2, 1. And for 6, you will have, by performing some number of moves, you'll eventually reach 3, 2, 1. And for 7, you will reach, and so on. So now this problem is asking, uh, you have to show that the final configuration is unique. So what do you think this final configuration will look like? Look at the final configurations obtained here and then, okay, first of all, how many columns will be there at the end? What do you guys think? Anyone?
Um, I came a bit late. Could I have a small recap if that works?
Yeah, sure. I was just doing this problem. This is
Okay.
the first problem and there was like nothing really, nothing else done. And we have just done a few small values of,
Okay, so like
Okay.
from
Could
this,
you go back to that problem? I'll just take a quick screenshot.
sure.
Yeah.
Okay, someone was saying something?
uh, at most one number appears twice, and like they're consecutive, I think. So
I think that if n is greater than or equal to some number x into x plus 1 by 2 means the sum of consecutive, then the number of columns uh, will be at least x plus 1.
Yeah, that's correct. So let's say you have somewhere like 16 columns, oh sorry, 16 pebbles. So this is basically what, like the fifth triangular number is 15, right? So this will have at least 6 columns. So do you have any idea of how you can prove this? And also Avni said, uh, two numbers can be consecutive, right? At most. And only two numbers can be the same. So what do you think is a way to prove this?
Can we prove it by induction?
No, it's actually much simpler than that. You have a condition. Okay, fine. First, so what she said had two parts, right? First of all, she said that one number can occur at most twice. and only one number can occur twice. So like if you have, let's say, n and n, so now there will be no other number, like k will occur at most once. And if this n comes twice, then it has to be consecutive. So what would it be if it were not consecutive? Let's say there was a gap. So what would happen?
The differences would be decreasing, but but in the end, like it should have increased at some point to make it equal.
Yep, perfect. So these have to be consecutive. And what if there are three of them together? How would you reach this kind of configuration? What would be the one just before this, let's say?
It would have been n plus 1, n minus 1.
Yeah, and n,
It's not
n
possible because
exactly.
the differences.
Yep. So either this one would be less than this, or this one would be less than this. So yes, your claim is correct. There will be only two numbers that occur twice. Okay, so now we have this triangular number idea and we have this thing. So what next? If you look at 7, this is coming out to be 3 plus 2 plus 1 plus 1. So how can you write a number in this kind of way? Like using triangular numbers and this. So we have a minimum number of columns as the triangular number, right? So what is the maximum number of columns?
How you have proved that only one number can occur consecutive?
Oh no, we haven't proved that yet.
So if you're interrupting, like what's the triangle number?
Triangle numbers are basically numbers of the form. Like the x triangular number is equal to x times x plus 1 by 2.
Ah,
Wait, so how do you prove that the triangular number should be the minimum?
So like you have, let's say, I don't know, 11. So now this is greater than 10, right? Which is the fourth triangular number.
Yes.
So assume you have 4 spaces. And now this last one, if this was 2, then this one would be, then there would be like one more move, which would create one more column, right? So this has to be 1. Now, if this were 3, then this would create this one more pebble would go from here to here, which would make this 2 and make one more column here. So this has to be 2. Similarly, this has to be 3 and this has to be 4. But now the sum of these is actually 10, which is less than 11. So there have to be at least 5 columns.
Okay. So can't we like use the same argument for the maximum? Like the next triangular number should be the maximum? Or can you make
Because,
a tighter bound?
for example, if we have, let's say, 12, right? And okay, no, sorry. Um, you have, let's say, 5 things, and you want to prove that 9 does not go into these 5, right? So 9 is here. So how do you prove that this won't happen?
Like you can argue backwards, I guess.
Go ahead. How?
So like if there's a 1 in the big last,
Yeah, there has to be one last. Yeah.
then Then there should be like 8 in the previous 4. 8, sum of 8.
Yeah.
And but the minimum that should be there is 1 plus 2 plus 3 plus 4. Because you can repeat the 1 only once and then the rest should stay constant. So
Why can we repeat the one only once?
we can only repeat the 1. Like you can't repeat any other number, right? Wasn't that the claim?
No, the claim, like we didn't prove that part. We just proved the part that if two numbers occur together, they have to be consecutive and like number can't appear thrice. So, okay, assume you have this kind of configuration. What is the issue? This is summing up to 10, but like let's ignore that now.
Wait, shouldn't have been then like 3, 4. Okay, no, sorry.
If we go backwards, we'll have three consecutive twos, so that this is not possible.
Three consecutive twos.
Like the second, third becomes 4-2, and
Okay, you're saying
we
this
have a 2.
becomes 4-2 and this becomes 2-0. Yep, that's correct. That's basically the idea. You can't have this because we proved that this is not possible. So that implies that we can't even get this. And like if you claim that this went here first, then that would imply that this is 3-4-1-1-1, which is like again a problem because of this and this. Okay, so if you have, let's say, n, and then you have like n minus 1, n minus 2, blah, 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 and then you have again a k. So can you generalize why this doesn't do?
So the goal to prove that it doesn't work is to find a situation where you have three of them consecutive numbers.
Yes. It's a similar argument to this. Yep, it is this. It is actually the same argument as before. Um, you can't like this to this is not possible, and in the same way, this to this is not possible because there would be an increase in the number of pebbles. Do you get the idea? Does everyone get it?
Yeah.
Could you like say like for the k, how do you like move backwards? Like how would the k not?
So basically, we are assuming that this is the final state, right? So this is basically
Yes,
consecutive.
correct.
So before the k, there would be k, uh,
K plus 1, yeah, that would be.
yeah, k plus 1. But the point is that if this goes backwards, then it's like k minus 1 and k, which is like not possible. And if this went here, this would be k plus 1 and k minus 1. And this would be k plus 1. So it's basically kind of an induction thing.
Oh
You
wait, but
just,
we assume that k and k was the first last.
yep, yep. So yeah, so we are done with this part.
I'm lost. Why are the numbers consecutive?
No, they have to be consecutive because like if they are, let's say there's a difference of 2, then this pebble would just drop here, right?
Yeah, makes sense. Yeah.
Yeah. So now we have these two very helpful things. So what can you say about the configuration now? Let's say you have 15, or not 15, or something like 18. So what would you say about the final configuration of this? We know that there are exactly 6 columns because 18 is greater than 15, greater than less than 21. And we know obviously that the last one is 1. So now what next?
I think we like construct the triangular number and then how much ever that is above the triangular number, we just add that to the sequence.
Yep, that's correct. So you have 1, 2, 3, 4, 5, like 0, 1,
I'm
2, 3, 5.
distributing it all over.
Yes. So you just take 2 over here, 3 over here, and now we have like added 3 to 15. This was 15, and we added 3 to it. So now this remains the same. This is basically the final configuration for all in. Uh, so if you wanted to be specific, you could just say it like if x is greater than k plus 1 by 2, or then you consider x minus this we need to specify. So there will be k plus, for this arrangement, there would be k plus 1 columns, and the final y columns will have plus 1 added to them, where initially there were 0, 1, k. So this is basically the final configuration. And if you have a triangular number, like say 21, then it's just basically the numbers themselves. Okay, so we're done with this problem. Did everyone get the idea?
Yeah, it makes sense.
Wait, how do we prove that the final configuration was like the same for like any steps?
The final configuration will be the same for any steps because like does it really, does the order of the steps really matter? I mean, you have to get we given the claims we had, like n and n is there's only one possible, and we can't have n and n minus 2 in the final configuration, right? Because then this would just drop here.
Yes.
So the order of the steps doesn't matter because the last one is forced, and then the last one in turn forces the one before it, and so on.
Okay. Okay. So we
Yeah.
just like reversed it.
Yeah.
In any configuration, we cannot have more than one repetition, right?
Yeah.
Okay.
Okay. So we're done with this problem. It was surprisingly, it is actually a C7. I think I told us was somewhere in the middle. But it is quite
You to,
doable.
you told C8.
No, this is C7 only, 2001 C7. Let me add the source here.
These
Okay.
days, such problems are very hard.
Sorry?
These days, such C7 like problems are very hard. No?
Yeah, these days C7s are much harder than this one. But it's still cool, like you can just say that I've done a C7.
So wait, at any point of time, this n consecutive will hold, right? Like only one n consecutive at any point in this sequence.
Uh, yeah.
Not just in like the final configuration. It'll hold like everywhere.
Wait, no, like you can, I mean, in somewhere in the middle of the sequence, like let's say you have, I don't know, 15. So then this could be changed to like 11 and then 4, or okay, let me just take some. But basically, you could have like 4, 4, 2, 2 in this sequence and somewhere in the middle. This is definitely possible because then if this is not the final configuration, we can perform moves on this to reach here, right? These are not consecutive basically.
Okay.
So you can have two different consecutive numbers somewhere in the middle. But in the final configuration, which we assume for our claim, it's not possible.
Got it. Yes.
Okay. So should we move on to the second problem?
Yes.
Let me paste it. Yeah, okay. So I'll give you a few minutes to try this. Processes problems look like invariants because most of them are invariants. Most of them are invariants. Okay, so any ideas? A mod 3 argument. Yeah, that is the point of the question. What do you mean by mod 3 argument?
Maybe we could try something where we assign a number to each configuration using binary, and then each removal will change it by a multiple of 3.
Is that true? Let me just see. If you have like
So
4.
just tried one example and it seemed to work.
So like if you take n equals 4, so then what are you denoting this as? Like 1, 1?
Yes. Then this will Or I guess zeros.
Okay, so all are zeros.
Yes.
Okay, so then this becomes, let's say, wait, what? No.
Or actually, all ones might be better.
Okay. But this would become, I think, BW, which is 0, 0, 1. So this was, what is this, 15? And this is 1. So what is your point?
Ah,
So basically, I think if n minus 1 is divisible by 3, then it will all, uh, like if we checked 4, 4 doesn't work. So all n minus 1 which are divisible by 3 convert to 4 once.
That's, I mean, you have to prove that 4 can convert to all n minus 1, not because it's possible that for 7 you reach a different configuration with 4 markers, right? You don't have to have WWW.
No, but that's what I'm saying. There, it is always happening that 7 will always become 1, 1, 1, 1.
No, that's not necessarily true. Let's say you have, let's take a smaller example, like 6 markers, or let's do 7 only directly. Or this becomes WB, which then becomes, sorry, wait, I think this is true. Okay, wait. Okay, let me just construct a counterexample.
What about constructing like blocks of 3 or something?
Blocks of 3, like,
But like we remove one, so
yeah, yeah, better.
I think actually does it changes by a multiple of 7, and so then we get that 2 to the, then it'll actually be mod 3 in n if these numbers we assign are changing mod 7.
Mod 7. Okay, wait, let me see. So you have basically got, you have these 4 configurations, right, basically. Uh,
Yes. Wait, but hmm,
so this would be, this changes to BB, this changes to WB, this changes to BW, and this becomes, uh,
but only works in some cases it seems.
so this will change mod 7, right, because you're changing 1, 1, 1 to 0, 0. But you're also, wait, you're also dividing everything before it by 2.
Yeah.
If you just get a proof, just come back. Let me just do this thing once. This changes to be,
Yeah, I got an counterexample.
yeah. So basically, it's not necessary.
Hmm.
Okay, you have these 4 states, right? So what can you say about this? Like, uh, so like I said earlier, processes is mostly invariant. So what invariant are you finding here? There's this monovariant, obviously, that after every step, the number of markers changes by 1. But what's the invariant?
The number of black squares mod 2.
Yep, that's correct. The number of black markers mod 2 is an invariant.
Might not be helpful.
Sorry?
I don't think it will be helpful though.
Oh no, it is actually helpful. Okay, wait. So the problem asking if and only if n minus 1, right? So first, let's try to find an argument for like 2 and 0 mod 3. So if we have, let's say, 5 markers, what can you say about this?
We can
It's similar to what Shubh said
cover
earlier.
the second marker.
Oh, sorry, I didn't catch that.
There's at least one white in the ending, but not that useful.
Is there, like if you have
Is it
W,
convertible
W,
to two
W,
markers?
So black left.
yeah, you can convert this to 2 markers. Okay, but
Oh,
can
yeah,
you
sorry.
realize this? Like, can you convert n to n minus 3? Like
Question
just
asks for possibility.
what?
Question asks for possibility that can it be reached to?
No. It's like just find a process that converts n to n minus 3. It's just
Yeah,
play around
okay.
with this.
Yes.
N minus 3 meaning like it should be just like WW.
Yeah, or in general, like yeah.
I think I might have found one, but if we take the second one,
Yeah, okay, let's do this. Okay, so we take the second one, so this becomes B, B. Okay,
then now we take the third one,
yeah,
and now we take the second one again.
yes. And this obviously works because like if you add W's over here, nothing is changing.
Yes.
So we have like for n equals 3, we have W goes to BB, so 2 markers are left. And for n equals 5, we just like, I don't know, do something random to get BB, WW, and then this goes to BWB, which then goes to B,
WW.
WW. So basically we are done for all 0, 2 mod 3, right? Because we can always convert anything 2 mod 3 to this state and anything 0 mod 3 to this state. Okay, so now let's go back to the n equals 1 mod 3 case. So you have the number of blacks are invariant, mod 2.
Wait. So then if we got one of these to go into just two different ones, then we would have had how many steps, which was 2 or 3.
Sorry, like what are you trying to say? Like different ones as in?
Yes, as in if we get it into, if there is a way to get it into just two different ones, then the number of steps would be 2 mod 3.
Yeah, Okay, so let's go back to the four states. Okay, so now that we have this, what can you say about the letters over here and over here? So first of all, notice that any operation on this is not affecting either of these groups, right? Okay, so like it's not affecting any of these groups, like yeah.
Yes.
Okay. So now you have that. Let's consider a different type of invariant. The number of black markers before and after a certain white mark, right? So if you have, let's say, you give every marker this kind of assignment, every white marker an assignment of the number of black markers before it. So this would be 0, 0, 0. And then if you have a black marker here, let's say, then this would be 1 and so on. So now if you look at in
The
all of these,
number of black markers just before it or all the black markers before it?
all of the black markers before.
Okay.
So now if you look at this, this is unaffected, right? If the numbers on all the markers are unaffected by any move, because the black markers after it are changing, not the ones before it, right?
Yes.
Okay. And what can you say about the ones after it? So first of all, let's consider blah 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 blah, and then you have k. Let's consider the first case. So this, if this has this marker has a value k, then notice that these two will also have the same value. So we'll have k, 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 and these will have something, whatever. So then after this move, these change to BB, right? So you'll have this again, and then these two, like these three numbers will all be eliminated. And for the ones after it, you will notice that,
Two more are added
yeah,
to each.
yeah. So if you consider the number of, uh, if you consider the number of markers, what can you say?
The number of what?
The number of markers, number of white markers, sorry.
It will have decreased by 3.
Yeah, okay. So here it is decreasing by 3. Okay, and uh, so like you have the mod 2 invariant and you have this kind of invariant, right? Like it's not an invariant yet, but like we're working on this. So you have these three, let's say these were 1 mod 2, and the ones after it are like anything mod 2. So now what can you say about the number of markers mod 2? Like if there were, before this, there were O markers with 1 mod 2 and E markers with 0 mod 2. So what can you say about that?
Which we're talking about white having the value, right? White has the
Yeah,
value.
only white has the value. The blacks don't have the value. So you can see that if these were odd, then O becomes O minus 3, and these are unchanged, and these are also unchanged because there are two B's. So these will, like, they'll have the same number of markers mod, black markers mod 2. So this remains E. And if these three markers were all even, then this becomes O and this becomes E minus 3, right? Do you get this part?
Okay, I lost you in this part. Could you please repeat it? Yes.
Sorry.
Like I lost you here. Like what happened here?
Uh, so if you have first we consider that we gave each white marker a value based on the number of black markers before it, and then we took that value mod 2 because we have found out that the black markers are invariant mod 2. And now we are just considering that for each configuration, what happens. So first we took this for an odd number of, if we consider that these three are odd, then what happens? And if these three are even, then what happens? So you have O minus 3 and E. Now what can you say about this case? So you have WWB, and this becomes BW. So for O and E, if these were O, let's say, let's just without loss of generality, let's assume that the first white marker is an O. So this will become O minus 2. And now there's a white marker with one black in front of it. So that becomes E plus 1. And these are unaffected because these ones are obviously unaffected, and these ones are unaffected because the number of these before them are the same. Then if we extend this, this becomes WW2. This has again O minus 2 and E plus 1, as we're considering this one as O. So these two are gone.
So difference is always 0 mod 3.
Yep, that's correct. So this, I'll leave the last case because like that's true. But like O minus E is equal to 0, sorry, is invariant. So this K value is invariant.
Yeah, invariance.
Yeah. So, okay, now what can we say? Like we have 7 markers, right? Like let's say, just say 7. So we have odd markers. There are, okay, this is not a good letter. So we have 0 odd markers and we have 7 even markers. So what happens next? What can you say about the final state now?
So then even minus odd stays like what 1 mod 3. So
Yeah, the even minus 1 is going to stay 1 mod 3. So now if you want to reach 2 markers, there has to be a white marker in the center, obviously. And you'll have like some markers over here or here. And we want even minus odd is 1 mod 3.
oh wait, so there will be a white marker at least. There should be one white marker, correct?
Wait, just like let's consider the cases, right? There's BWB, then there's WWB, and okay, so now in this case, there is 1 odd marker and 0 even markers. So this is not possible. In this case, now we had that the black markers are invariant mod 2, so this is also not possible. And same for this. And this one is just 3 even markers and 0 odd. So this is also not possible. So we are done for 1 mod 3. Did you guys get the idea?
Yeah.
So,
Wait, so why must we have a
So
W in the center?
oh, because we can't, if there's no, like in the problem, it states that, um,
Okay, yeah, I got it. So wait, so you
yeah,
assume that like the second last uh, configuration will have a W in the center to reach the last one.
yeah, it has to have W because in the question it states that,
And
uh,
yeah, it'll have 3 coins. Okay. Yeah,
yeah.
nice.
So the
okay,
motivation for
so
this
what
invariant,
was the process like for this problem?
the process came in an earlier part of the problem for changing n to n minus 3. And then
Oh,
again, we can consider like invariants are kind of processes only. So like basically performing a step and you're seeing what is changing. So we had this invariant of the number of bees is easy to get. And the motivation for considering this invariant is that we know that the markers before and after are not changing. So we might want to do something relating to the ones. For these markers, we might want to do something related to the ones before them. Because the number of bees is again not changing, mod 2. So did you guys get the problem? Oh, guys.
Yeah.
Yeah, I got it.
Okay, nice.
It is also a very nice solution with group theory. Like, basically for each, let's say for white coins you give it the group element A, and black coins you give it B. So each transformation, let's say the group element remains invariant. So like it's like A cube is equal to B squared. You get that BA squared is equal to AB and so on. And then you can notice that these are all elements from the permutation group.
I see.
And then after that, you know, you see the start state and the end state, and then you can see that they can only be the same one, and it's not equal to 1 modulo 3. And then after the induction is like the same.
That's cool. Okay, so now there's this thing in processes, or there's a trick called superposition. So what this means is that if you have, let's say, a game, like you have numbers 0, 0, 0, and you can convert any of them to 1, right? So this particular state can go to 3 possible states, which is 1, 0, 0, 0, 1, 0, and 0, 0, 1. And now let's say we want to reach a final position, or we want to like win this game basically. So for that, we want a strategy which works no matter what steps are used. So we'll define a superposition to be like basically considering all these states to be true at once. Do you get this idea?
Could you like repeat it?
So if you have one configuration that goes to many different configurations, and you want the strategy that works no matter what the configuration is. So you will just assume that all of the configurations are true at once.
Okay, got it.
Yeah, okay. So, okay, with this idea, I'll give you the next problem. Some of you might have seen this problem before. Oh, by the way, the source for the previous problem was 2005 C5. I'll let you guys try the problem for a few seconds.
This one is USMO 2015 P5.
I'm sorry?
This problem is, I guess, USMO P5 or something.
Yeah, it's USA TST.
Oh, yeah.
But do not be scared looking at the source. It's pretty simple using the trick I told you.
I have done it before.
Okay, if you want a buffer problem, you can try USA TST 2020 V3.
I guess for this, we just say
Again,
that all the states.
Okay, first of all the states are what?
Well, I guess if we take all the states where exactly I would say one electron is there in the entire system, and one electron is with any of the different atoms, we can show that if all of those are direct in the first place, which is true, then we can show that we can get that to be true later as well. By
Yep.
also considering what as the ones where there's exactly one hole, where there's no electron.
Yep, that's correct. That's the idea of this problem. So first 2015 is like unnecessarily large. Let's just take five, so four atoms, right? Now we have that each usamon either has one or zero electrons, so we'll just give it a value of 1 or 0. So you can have all 4-digit binary numbers. Let's do 3 because like I don't want to write everything. So you have okay. So
Does
now
the
you have
order
these.
actually matter?
Sorry.
Does the order matter? Because like you can do like any operation.
Yeah, the order doesn't matter, but like just for considering. Okay, so now what can you like? You can transform any 0, 0 to 0, 1. Sorry, wait, what? Oh, my bad.
I think it's any 1,
Yeah,
0
it's
to
1, 0 to 0, 1. So like you have this as an independent state and this as in one independent state. Now we'll assume, so superposition, for some of you missed it, so I'm just repeating it. In superposition, we have a given config and we assume if it can go to multiple number of configs, and we have a given strategy or process, then we'll just assume all those configurations to exist simultaneously. So that's superposition. So like Bhairav said, we'll consider the number of electrons. So these three have the same number and these three have the same number. So let's focus on this one. So we want to move all the electrons to the right, let's say. So now we do the process of taking an electron from 1 to 2 and then from 2 to 3. Right. So now notice that this will work for it won't affect this one at all. This one will be affected on the second move and this one will be affected on the third move, or second and third, first and second both moves. So finally, all of them will reach 0, 0, 1. Now we are also assuming that these three states are existing at the same time, right? So these will change to 0, 1, 1. This one stays the same. And this one changes to 1, 0, 1. So again, we want to get this one here as well. So we'll just repeat this same thing again. And this process won't affect this, but it will change this to 0, 1, 1. And now notice that we can extend this to like any number of usamons. So let's you have like 5 usamons and you have this configuration. So you'll just perform this process 1 to 2, 2 to 3, 3 to 4, and 4 to 5. You'll perform this as many times as it takes to get all the electrons to the right. So in the end, we'll just have, now we'll do it for 5. So you have 0, 0, 0, 0, 0. So all of these configurations you have exist at the same time. Do you guys get this?
Yes.
Okay, cool. So now that we have these 6 configurations that exist at the same time, what do want? Uh, we want to select 2 of these USMons such that both of them have the same number of electrons. So we need to guarantee that they have the same number of electrons, right? So if you look in this, what that basically means is that we want to select 2 indices from 1, 2, 3, 4, 5, such that their values are the same. We can remove this case and this case, since anyway, uh, no matter what 2 values you pick, they will be the same. But you have these 4 cases now. So yes, any ideas how to prove that, how to prove or disprove? Okay, I'll just go ahead because we're like slightly short on time. But basically notice that no matter which 2 elements you pick, they will either not be guaranteed or they will not be the same. Like only these ones are guaranteed. Like you know what you're picking because all of them are same. And in all of these, there's one element which is different from the rest, like at least one element. So, so you can never be sure of what you're picking when you're in these columns because all of them exist at the same time. So, and now we just want to prove that no matter what kind of step you perform on any of these cases, uh, it won't change this configuration basically. So you have 0, 0, 0, 0, 1. You have these 4 states. And now notice that if you switch, let's say index 5 and index 3, so this state changes to 0, 0, 1, 0, 0, 0, 0, 1, 1, 0. And now the final trick that finishes the problem. Can you guys see it?
And in any case, there'll be some point in which they'll disagree.
Yeah. So basically, if you consider the columns, right? If you look at the columns, they are basically the same. So what we can do is we can just switch the indices. So after any change, if you want to change index I and J, so you can just swap these 2 indexes after the move is performed and it will have the same columns. So basically you have not made any change. So if this state does not work, then no state can work.
That's the invariant.
Yeah, basically. So we can obviously extend this to 2015 as well, or just like take all the different states, all the different states where there are different number of electrons, and that finishes the problem basically. So did you guys get the idea of this one?
Yeah. Can you explain once the how did you use superposition in the initial example?
In this one,
Yeah.
you like basically superposition is just like assume all of these exist at the same time.
In this problem, I guess the superposition we have used to prove the contradiction,
Yeah,
which all those can be derived from other states actually. I think that's a good intuition.
sorry.
Actually, from any given state, we can reach all of these, at least one state of this form.
What do you mean from any given state? Like, could you give an example?
Any state of 2015.
No, like if you have the number of USMons with one electron is not going to change, right? That's invariant. So if you have, let's say, 10 ones and 2005 zeros, then you can reach from in any state from this configuration to any state with the same number of USMons with an electron. You can't go to like some state with 11 electrons.
Yeah, I'm saying that we can reach the state with 2005 zeros at the first and uh, say the two ones at the last.
Yeah, we can reach that kind of thing. But then uh, you are like the superposition is basically assuming that all of these are existing at the same time, right? So you are also performing that process on all of these states. So all of these states will also change accordingly.
I think is this process may be a motivation of this group.
Yeah, yeah. So all of you guys got this problem, right?
Yes.
Okay, nice. Let me see. There were like three more problems I was thinking of doing, but we have some time restriction, unfortunately. So I'll just do this really nice problem. It's pretty famous. I mean, some of you might have seen it. It's IMO 2021 P5. Where did it? Okay. So I'll give you guys 3 minutes to try this problem. Okay. Any ideas? People who have not seen the problem before.
Well, I guess that Jumpy is sort of carrying two of the walnuts that are, as in, by swapping them and then going to the next one, the two first walnuts are being carried sort of through the circle. So maybe if there's a time where the walnut number is greater than that, we could do something.
Uh, what do you mean is being like carried through the circle? I mean, it's not necessary that one walnut is carried throughout.
But if you look at it, this is a if we look at it, the first wallet is being swapped with the third wallet, and the second one with the fourth one, and so the first two
No, no, no.
wallets really.
It's not like that. They are like the order is not given, right? So if you have like you have one here, you can have three here, and you
Wait,
can have 2000 here.
oh
So
yes, but when
these
the
will be
wallet,
swapped in the first move, but like it's not necessary that three will be swapped ever again.
well, no, as in by the numbering of the holes and numbering the walnuts.
Yeah.
So then if we put the walnuts from whole 2021 and whole one will be carried throughout.
Uh, you're not like moving the walnuts based on the holes. You're moving them based on the number of the on the walnuts.
Oh, but then it doesn't. But then the holes don't matter.
No, the holes have no numbering anyway.
Oh yes. Okay, I see. So two walnuts adjacent to walnut cake. Okay.
Yeah, walnut key is like the walnut with number key on. So, okay, I'll just start with the problem. You want to swap walnuts such that A is less than K is less than B, right? So now this invariant is like the basically the key idea. You consider a walnut to be black if it has been moved and a walnut to be white if it has not been. Oh, sorry. You consider like if the kth move is done, you turn the kth walnut black. Like basically that's the point, not swapping. So for example, if you have 1, 2, 4, 3, 5 in a 5 walnut configuration. So initially all of these will be white, but then on after the first move, this changes to black.
So the kth walnut turns black.
On the kth move, yes.
Yes, okay.
Okay. So now what is the motivation to consider this? If you have this walnut 1, if it is, we basically what we want is that we want this kind of configuration where this white walnut is swapped, changed to black, right? Because that would imply if this walnut is black, then this would be less than this, and if this walnut is white, it would be greater than this. Like on the kth move, if this is true, then we're done, right?
Wait, is that true? Like, why would
Like if we have a walnut numbered case such that on the kth move this is true, then we are done. Do you guys get this? Because like if this is still white and it's the kth move, then this is greater than this because this walnut has not been used yet. And if this is black, that means it has already been used before this one, so it must be less than this. Do you get it now?
oh
You are considering. Oh, no, no.
Yeah. So we have this. Now basically just we'll just look at how the walnuts are changing. It's like you have W, W. This turns to, sorry, you were saying something?
I think it's actually important that 2021 is an odd number here because otherwise you could just or put a even numbered put the numbering like 1, then k plus 1, then 2, then k plus 1, and so on. If it's a multiple of 2.
Like,
K.
for 4, what are you saying?
Like 1, 2, 3, 4. In that case, it won't ever happen. Thing.
What? Like this changes to 1, 2, 4, 3, and then this becomes 3, 2, 1, 4. It happened. I mean, your thing is true, but I think you took the wrong order. I think it was something like 1, 3, 2, 4 does not work.
Yes, I wanted to say that. Sorry.
Yeah. So yeah, it's of course important that it has to be odd, but why is that? So if you look at this configuration, it has become like this. Now, if this walnut is swapped, then we are done, right? So we don't want to turn this walnut black or this one. So we'll turn off these black so that becomes, and now this becomes black. And now notice that no matter which of these we choose, we will be like done, right? So can you prove that this is true no matter what for any odd number?
It doesn't actually matter if we are swapping, if we haven't yet gotten a white and a black one, because then we're just swapping two of them which are identical. So we can
Yeah,
ignore the swapping part.
yeah, that is the point. Yeah,
So we can't, if we look at the first one, we can't use the two next to it until we have gotten both of the next two
yeah,
and so on. So then, since it's an odd number, eventually it will loop back around itself when we get two of these dead spaces next to each other. So we can't actually finish those.
yeah. So the idea is basically you consider the gaps between two black ones, right? That's what you're saying, right?
Yes.
Yep. Okay, that's correct. So we just want to prove that one even gap exists, like one gap of even length. And we can see this is true because like you have, let's say, I don't know, 9 walnuts. So after the first move, it turns to one black and then eight, a gap of 8. And now on the third move, this changes to 1. And now you're not moving the ones adjacent to it. So this like stays 1, right? And now you're adding one more one somewhere in the middle, one more black one. So now there will be a group here and a group here, right? So one of them has to be odd because their sum is 7. And similarly, if you have 3 walnuts, then you have 3 gaps, but you have the sum of 3 numbers is equal to 6. So again, one of them must be. Do you get the point?
I'm sorry, I didn't get it. Could you like say it again?
Yeah. Okay. So if you have, you consider the gaps in between two black walnuts. So if you have 9 walnuts in total, after the kth move, you will have k walnuts, and you will have k gaps as well. Like I'll just do it for a number so it's easier to understand. So on the first move, you will have one black walnut and you will have only one gap around it, right? So this gap will have 8 walnuts. Now, after the second move, you will have one black walnut. You will have some gap over here. You will have another black walnut and you will have a gap over here. And
Yes,
now these two gaps have 7 walnuts in total, right? So one of these has to be even.
correct.
And now if you change one of this walnut, you're basically lost, right? Because you have a white one here and a black one here. So you don't want to do that. So you change some random walnut in the middle. But then again, you have 3 gaps, and this time the sum of 3 numbers is 6. And if all of these are odd, then the sum will be odd, which is like a contradiction, right? So there must exist one even. And if you have something like, say, 1, 1, 1, and you add a black walnut here, such that there's no gap between these, you basically notice that there will again be, let's say there were k gaps on this turn, and there were, I don't know, x black walnuts. So on the next one, there will be k minus 1 gaps, and there will be x plus 1 black walnuts, which implies that there will be 9 minus x minus 1 white walnuts. And on the previous move, there were 9 minus x. So notice that the parity of this is, the difference between the parity of this is the constant.
So like eventually the number of white walnuts will stay even. Like there'll be one set of white
Yeah,
walnuts which is even.
yeah, there will be one
And
set
that
of,
completes it because we need just WW black.
yes.
Okay. Thanks.
So did everyone get this? Or the final idea like, of the even gaps? Okay, I'll take that as a yes. So it's almost 8:30 now. Do you guys want, are you guys free for like 10 more minutes? I could explain one more problem, or I could put that problem in the piece set instead.
One problem is fine.
Sorry.
One more problem would be fine.
Okay, if you guys want to leave, you can leave. I mean, this recording will be available. Uh,
Will you like put that problem in the P set as well? Like just like so that the people who are trying the P set can also try that if they have not seen the video.
yeah, sure. I'll just, instead of putting it in the piece set, I think I'll give you the sources of the problems.
Fine.
So you can attempt those. I'll do, okay, I'll give you guys a choice, 2009 C5 or 2018 C3. Let me just,
2018, C3.
okay, so 2018 C3. Both of them are actually equally hard. So like 2018 is more recent, you know. Okay, this is the problem.
Well, I think this was discussed by Rochelle in previous classes, so you can take another question.
It was? Okay, okay, then I'll do 2009 C5. 2009 C5 is actually easier, by the way. So So I'll give you like 2 minutes to try.
I think this was also discussed.
Seriously. Has anyone done this problem? Reply, guys. I mean, anyway, it's 8:30, so it doesn't matter.
Like the previous problem, like Rushel did it, yes, but this one I don't recall.
Okay. So anyway, those who have done this problem before, you can leave. Those who have not done it, you can stay and try the problem. I'll just stop recording.